All right, this video today that we're going to look at talks about the tangent line problem, and this is going to be one of the main topics we're going to cover in calculus. So you really need to make sure that you understand this concept because this is going to be applied throughout the rest of the semester. Before we start, we want to recall the slope of a line. We know that delta y over delta x, or change in y over change of x, is the slope. And more specifically, this is calculating the rate of change of y with respect to x. And when we find this rate of change of y, uh, delta y over delta x, this is what we call an average rate of change. So for example, we know that if we have a line here and we want to find this average rate of change, we're looking at the change in y over the change in x. So this is giving us what's an average rate of change. Well, the problem that we're presented with here today is we're given a function y equals f of x. Now we want to find the instantaneous rate of change of y with respect to x. Okay, so now we're not looking for the average, we're looking for the instantaneous rate of change at any point p x f of x on the curve. So if you notice now, we don't have a straight line. Our graph is some type of a curve, and we want to find the exact rate of change at this point P. Okay, so we want to know how is this function changing at this point. And we want to be able to determine the instantaneous rate of change at any point along this curve. So to do that, first of all, we want to choose a point Q that is close to P. So if I go up here, I can pick any point here. Now realize when I pick this point here to be point Q, you may look at the graph and say, well, that's not really close to P. But I really want you to know I'm kind of zooming in on this so that we can actually see this a little bit clearer. Really, when I pick point Q close to P, I really want to be picking something here that is extremely close to P right here. But if I make it too small, you're not going to be able to see this. So I'm going to realize that this is extremely close to, point Q is extremely close to P. It's just that we've zoomed in so that we can visually see what's happening. So if we pick this point Q, and this point we're going to call x plus delta x because the distance we're going from P out to Q, this is going to be a distance of delta x. So in other words, at point P, this is x, and if this is some distance, for example, if x is 4 and then delta x may be 0.1, then we would be over here at 4.1. So our new point is going to be x plus delta x. That's our new location. So that means point Q, the x coordinate would be x plus the change, which is delta x, and then our y coordinate would be the function f evaluated at x plus delta x. Okay, so keep in mind these are just representing your x and y values. So f of x is your point P, x plus delta x, f of x plus delta x is our point Q. So now that we have a point Q that's close to P, we want to find the slope of the secant line between P and Q. So for example, that means if I draw a line here that goes through P and Q, we want to find the slope of this line. Well, if we recall the slope of a line, we know that we can find the slope of a line by taking y2 minus y1 over x2 minus x1. So if we use our slope formula here, it's just that we're going to look at this as being x1 and y1, and point Q is going to be x2 and y2. So if we take our y2, that means down here we're going to take f of x plus delta x that's representing our y2, minus y1, and up here at the top our y1 is simply f of x, and that's all divided by x sub 2. Well, our x sub 2 coordinate is x plus delta x minus x sub 1, which is x. And here you're going to notice what happens. Well, if we look closely at this, we can simplify this and we would have f of x plus delta x minus f of x all over, the x's are going to cancel out, so you're left with, on the bottom, delta x. Now, if you think about this, that makes sense. On the top is your change in your y, so on the bottom, delta x represents the change in x. Just like our notation up here, slope is the change in y divided by the change in x. So the slope of this secant line is going to be f of x plus delta x minus f of x over delta x. So that's here the slope of the secant line. Now keep in mind, this here is the average rate of change of y with respect to x over the interval x to x plus delta x. Okay, so what we found here is going from x to x plus delta x over this interval, we have found this average rate of change. Now, because point Q, remember, this point Q is really extremely close to point P, this is an approximation to the instantaneous rate of change at point P. So remember, the initial part of this problem was to find what is the exact instant rate of change at this point P. Now let's look at a third step. Let Q, if we let point Q get closer to point P, now if we think about that, down here we said this was delta x, the distance between point P and Q on the x-axis. So what happens as Q gets closer to P? So for example, what if I move point Q here? So now we have, here's our tangent, our secant line, and then if we move Q closer, we have this line. And then what happens if we move Q even closer and closer? And if we move Q close enough, what's happening down here to this delta x? Well, as Q gets closer to P, delta x is getting, this distance of delta x is getting smaller. So that's why here delta x is approaching 0. So what happens as delta x basically goes to 0, point Q then essentially becomes point P, which means we actually find the slope of this tangent line at point P. Now if you think about excuse me, if you think about the previous chapter, this looks familiar. If we want to calculate what's happening here, delta x is approaching 0, and that should sound like our limit. So if we look at the definition here, this is the derivative of our function f, where f prime, the derivative of function f is the function f prime. So this little prime mark here indicates the derivative of the function, where f prime of x is the limit. And what's this here? This here is our rate of change, f of x plus delta x minus f of x over delta x. That's what we just calculated above. But we said what's going to happen as this delta x approaches 0. Now we know that we can't plug 0 in for delta x because that's going to give us 0 in the denominator. So we want to find the limit as delta x goes to 0. And when we do that, That's going to give us the slope of the tangent line, which is the instantaneous rate of change of y with respect to x. So this is the whole idea of this topic here. We want to be able to calculate the instantaneous rate of change at any point on this curve. Okay? And to do that, we're going to take the limit of our function evaluated at x plus delta x minus f of x divided by the change in x. And we're going to look at how to do this in the next video, how we can actually determine this derivative. And once we find the derivative, that will allow us to find the instantaneous rate of change at any point along this curve.